The work in Servant was joint work with Zonke Han, who's over there, and Altmestano Gulari. Andreas Loh helped considerably after the first release, as did the Haskell team at Anchor, which was one of the first commercial users of Servant. And I think this Servant is a particularly appropriate topic to discuss here because on the one hand, it's solving a very practical industry problem, namely writing web applications quickly and easily and safely. But on the other, it's using some ideas that, though they existed in some form in academia already, I think Servant's the first case that applies them in practice to a library. And these ideas, that's the type-level DSL side of it. These ideas are really interesting, and I also want to, in addition to discussing Servant as a library, also discuss this technique, which I think can be applied in a wide range of circumstances. So I'll talk a little bit about what it is that motivated us to do Servant, to what idea, what view of what web development should be like led us to try to write this library. And then I'll switch gears a little bit and talk about a much simpler, and give some examples as well of what it does. And then I'll switch gears and talk about a much simpler type-level DSL that hopefully will be much easier to understand and will really bring out the basic essence of the technique and also the advantages therein. And hopefully, even if you don't use our library, you'll consider applying this technique in other circumstances. And then, to the extent that I have time, I'll also talk about how we implement it practically, how we transform these ideas and transfer them into the context of web development. So, let's talk about the main idea. The main idea is roughly this. In web programming, web APIs should be a central concept. The description of a web API in particular should be a central concept. And in a sense, this is already the case. If you observe, if you witness people working on APIs, web programmers will very often talk about their API and discuss it at great length. And in fact, often that's the business requirement is, this is the API, this is how it has to look. And so, in a sense, making that central it accords with the practice of development, and that's one thing that it has going for it. But currently, web frameworks don't do this. If you look at the code the code written with most frameworks, the API itself is only implicit in the implementation. There's the routing section, and that's part of what the API is. But the rest of it, what the request body looks like, what the response body looks like, what the headers that are expected, they're strewn all over. The handler handles part of it, the routing handles part of it. And we wanted to, and it's an unfortunate circumstance, I think. Now, the second reason is that it's much easier to modify. With the description of the web API, if you change something, at least in the case of Servant, you get type errors wherever things need to be modified. And for those of you who are Haskell programmers or Camel programmers, this will be a familiar and very desirable trait of programming in these languages. But the third reason, these are both sort of, you'll have to take my word for it, or you'll have to experiment and see whether you agree with me points. But the third one I hope to make very concrete and might be the most important. And it's that web API descriptions are a reusable component, and one that we want to reuse. We want to reuse it in a variety of circumstances. When we're writing a web service, we want to be sure that we accord with the specification, and we don't want to repeat ourselves about the aspects that that go into it. When we're writing documentation, we also need it. And I'll show you some examples. Documentation will be the first one. To make this more concrete, I'll give a simple example, a simple running example of a service that just wraps a counter. And it'll have two endpoints. If some aspect of this is unclear because it relates directly to web programming, please interrupt me and I'll explain. As I said, I think there are lessons here that are relevant quite outside the context of web programming. So we have two endpoints, and this is the informal description of what we want our API to look like. With Servant, we can formalize this description. We can write it in a formal way in a DSL, which is the Servant DSL. And it looks like this. As you can see, we had to be specific about a couple extra things. For instance, we had to specify that JSON is the way in which we encode our response. If we had other content types, we would put that in that list, in the type level list. We also stated over there that step is the URL that the post will. So these two elements correspond to the two endpoints. This last one corresponds to the combination of both. That symbol in the middle that we call alternative combines two sub-APIs. We still have to define what counterval is. That's a type. That's a Haskell type. So what this is saying is there's a get endpoint that returns a counterval, whatever counterval is, serialized as JSON. And then there's another endpoint that responds in the step URL to post requests and doesn't return anything. So we need this we need this code to get going. We need to declare our data type. In this case, it's just a new type wrapper over integer. And we need the appropriate class. We said that we will be returning JSON, so we better be able to serialize this into JSON. A technicality is that we need, if you take a look at the section up here, you'll see that all these things are types. But we'll also be working at the value level, and we need a value level proxy for our type to get going. And then this last section I'll explain in a second. So now we have a formal description of our API. I haven't described what the servant language looks like. I will towards the end in a more formal way. But we've used the elements of the servant DSL to give a formal description of our API. And given that we have this, we could hope to get a lot of things for free. We could hope to get documentation, for instance. Very often when you write a web API, you need to document it for your users so that they know how to interact with it. And this can often be a painful and error-prone process. You sort of have to look through your code and see what it does and hopefully get it right and hopefully maintain it. But if we have a formal language, we can just hope to derive it. And using these two functions from the counter API is, as you'll remember, the value level proxy for our type, which represents our API. With using Markdown and docs, we get a Markdown representation of our API. This is just the get endpoint, but the post endpoint looks similar. And here you can see where toSample was used. We had to give a sample counterval so that the documentation could be generated. And so now there's this wonderful scenario where, as you'll see, we'll be using this API description for everything, for writing our server as well. And we can't go wrong. We can't go wrong, and documentation can't get outdated because it's generated automatically. Similarly, we might hope that we can generate client functions to query our endpoints. And in fact, we can. I wouldn't be mentioning if we couldn't. We have to give a second argument to the client function that we provide, and that is where the base URL is for our service. And then we pattern match to get two functions that are the client functions. By the way, this isn't code generation. This is just a higher order function. And again, this can't go wrong. If we update it, this gets updated as well. And if we add an endpoint, then we'll get a type error because our pattern match assumes that there are two client functions, but there will be three, say. This is the type of our functions that we get. And it's exactly as we would expect. It's very nice to program with this. Finally, we can also hope for safe links. If you have some HTML and it has a link, an href to something, you often get this case where the link gets outdated or you got it wrong and you get a 404 whenever someone clicks on it. But if you have a description of your API, again, you should be able to check whether a link is a member of that API or not. And we have a function to do this as well. We use a proxy we use the proxy that we already have for our entire API, and we have a proxy for the link that we want to generate. And if that link is part of our API, then we get a link. This is not actually a string. It just, when printed, looks like a string. And if it's not a member of our API, if we try to do something that doesn't exist, we get a type error. Now, in my opinion, this is the best example of a smart constructor. You don't need a maybe. You get a type error if you can't generate it, if you shouldn't be able to generate it. But of course, the main thing that everyone's interested in is writing servers themselves. And again, we have a description of the API, so all we should have to do is write the handlers. Everything else we've already described. So we write the handlers. The server get counter and server step counters are types synonyms or associated type synonyms that will get resolved into something that I'll explain in a second. But as you can see, these two handlers are barely aware, are not at all aware of the fact that they exist in the context of a web API, because we've already largely handled that aspect of it by describing the API. And then we combine them, and we initialize the tvar that we're using, and that's a server, and it'll conform to a specification. It'll reply in the correct endpoints and whatnot, and do all the things that you expect web frameworks to do. That's a slide. So I hope that gives a sense for why it is that we think that abstracting away this notion of a description of your API is an important one. We get all these things that work with Servant right now. But there's this lingering question of how do we get this done? And you probably already have a sense from the title of the talk and from the examples of before that we have a DSL that exists at a type level. And with the terms in this DSL, you can create an expression that represents your API. So let's talk about these type level DSLs. Let's start with something very simple. Here's an expression in simple arithmetic DSL that has just add and 1 as its terms. And I imagine most of you have either written something like this or know exactly how to interpret something like this. And generally the answer is this, or something like this. This is easy, and it's great, but I never said that this was a value level. This is actually a type, so that won't work. So let's try again. Let's imagine how we would interpret this as a type. It turns out that the answer isn't that much more complicated. We write a class that represents our interpretation function, We need a value level proxy to figure out which instance to pick. And we sort of give the same signature that we had before, almost. And then we simply write instances for it, for the terms that we want to interpret. We also need to declare empty data types. We don't care about the value level. We're done with that value level for now. So our data types don't actually, they're empty. And as you can see, this isn't that much more complicated than our value level DSL. And you might think, whoa, cool, but this is just a parlor trick. But it really isn't. There are two big advantages to doing this at the type level. One is that it's extensible. It's extensible along two axes. In our value level DSL, if we wanted to write another interpretation function, we could. If we wanted to pretty print, we could just write a new function that would do the pretty printing. But if we wanted to add a new term, we'd be in trouble. If we had been provided with a library that contained the expression data type, and we couldn't touch the library, we'd be in trouble because data types aren't open. So this is known after Philip Wadler, I believe, as the expression problem, or this is one manifestation of the expression problem. And type-level DSLs solve this. Because if I want to add a new term, I just declare a new data type, mult, for instance. And then I just declare an instance for it and interpret it. So that's cool. But there are other solutions that solve this problem. The great thing, the other great thing about type-level DSL is the second advantage. And it's that we're on the right side of the phase distinction. So this is, we're talking about Haskell, which doesn't have full dependent types. So our types are not allowed to depend on values. And this is important. And this is important for reasons that you might already be seeing, but that will become clearer in a second. But roughly, look, we have an expression that represents, let's go back to the servant DSL in our minds. We have an expression that represents our API. Now, it could have one endpoint, it could have two, it could have three. And in order to generate a server from this expression, we also need the handlers. And the number of handlers that we need varies with the expression. And in fact, the type of the handlers themselves varies with the expression. So we need to be able to do this. We need to be able to vary what we expect in order to generate a server, depending on the expression. And that means we need to vary the types. So let's look more concretely how this works in a vague extension of our simple DSL. We now add a hole. And the idea behind a hole is this. Whenever you see a hole in your expression, in order to fully evaluate it into an integer, you'll need to provide another integer. So, add hole and hole will require two integers. So now we can see how the types vary, right, depending on the expression. And we can do this. We now have a different evaluation function. We need an associated types in them that allows the instance to declare how the types vary. And if you look at this, if you imagine value AR being just R, you'll see that it looks a lot like our original eval function in CPS form. But of course, value AR doesn't have to be R. In the case of 1, it's basically just a CPS version of our previous interpretation, or of our previous instance. In the case of add, it is too. It gets a little bit uglier because it's CPS. Now, wait, let me see if I can get this. Well, yeah, there we go. And so now the case of whole is the interesting one. The case of whole is the interesting one. Sorry, it's blocked out. I don't understand Macs or computers. The case of whole requires an extra integer in order to evaluate. And so we get something like this. Look, so here we have another expression, and it has a whole. The expression has a whole. So once we eval it, we should expect something of type int to int, because we have one whole. So that means we need an integer in order to get back an integer. And if we have two wholes, then we can get something of type int to int to int. And this is I think the big advantage of having type level DSLs. So now I'll go a little bit into the servant language itself. I gave you quite a few examples of the things that you can do with an API description in the servant DSL. And each one of those corresponds to an interpretation function of the DSL. And so similarly, each one of them has a class associated with it that does the interpretation, much like our eval from a moment ago. And quite a few of them have slightly different approaches, techniques involved in order to get them going. But of course, it'd be too much to talk about all of them. So I'll just focus in the case of the server interpretation. So let's talk a little bit about the servant grammar. I've simplified it somewhat. And importantly, it's extensible. Remember, you can always add new terms. And this turned out great for us because it basically means that we have a plug-in system, a very nice plug-in system, where that we know is nice because it's what we use to write the library in the first place. So it's not like there's some second-class citizen that's a plug-in system. This is actually what we use to write the entire library. So you can express, we can't foresee all the things that you might want to express about your DSL. You might have very strange dependencies between status codes and the request and response bodies or headers, all of these things that we can't foresee, but we don't have to because you can write new terms yourself. But still there's a core that we've realized is important to provide out of the box. So we have API, which is the top level. And we have this alternative combinator that combines two APIs. So if you have a sub-API with 4 endpoints and one with 2, you can combine them and make a larger API. And then we have this item, and that combinator over there, Zonka calls bird face. Yep. And that basically applies something to the API. So we have some examples over here. Symbol, for instance. Symbol is just a Haskell. I'm implicitly assuming a lot of Haskell extensions, type operators, and typelets. A lot of them. And so we saw this before. The step URL was a type level literal, and when we combine it with birdface, then we say that the entire API on the right-hand side will be served under that URL. And we can combine multiple ones. And another one is request body. A request body has a set of content types and then a Haskell type. So I can say, look, the entire API on the right-hand side, which might be just one endpoint, but it might be multiple ones, all of them expect a request body. And the request body should be deserializable into the type that I specify as the second argument. And the content types that I accept are a type level list, the first argument. And all of this is type safe. We type check to be sure that, in fact, we know how to deserialize that type via the methods that you specify. Capture is something that will also be familiar to web programmers. If there's a URL, you might want to get it out. It might be someone's ID, it might be someone's name, someone's age. That second one should be type instead of S-type. So we again have to deserialize that. And we always serialize with the same class in that case from text. The symbol over there is used for documentation purposes only. And then we have the methods. Each method on its own is already an entire API, but of course it can be combined with other things. We have the usual ones. We have more. We have raw, which is interesting. We can combine other Haskell web applications written with other frameworks as a sub-API. Well, some web frameworks, not all of them. Type is just a Haskell type. Content types is a type-level list of Haskell type of content types, some of which are, for example, plain text, JSON, HTML. So this is a fraction of the terms in the language, the non-terminals and the terms in the language that we ourselves provide. But there's more that we provide, and there's more that you can write. And this is the class that we use to provide the server implementation. As you can see, it looks a lot like our val prime. In particular, it has an associated type synonym. And that is used as a second argument. Again, we have the proxy in order to figure out the types and whatnot, but the important argument is the second argument, and this is interesting. We get to vary the type of the second argument. So in the case of, say, get something, then we expect something of a particular type, the type of the handler, a single handler. But if you combine two gets, then we expect a different type, which is a combination of two handlers. So we get to vary that. Routing application is, can sort of, yeah, I'll skip over it. Basically, the essence of it is that once you have an API description, you have a tree of sorts with an implicit root node. And so when we're routing a request, we sort of go through the tree and trying to see whether something matches. And if something matches, we return that. And if it doesn't, if nothing matches, then we return a 404 or whatever. But we have to sort of like look through it and see which one combine in a sort of monoid way to see which one we should respond with. And routing application is basically doing that. So a particular instance, a particular interpretation of a particular term that's worth looking at is get, the get method. But I'll simplify it a little bit. As I said, you can have a list of content types. And we'll check that each one we know how to serialize. In the case of the request body, we have to be able to deserialize a value. In the case of the response, the method, we have to be able to serialize the value. And we do this for any number of content types, but I'll simplify it a little bit and assume that we are using just plain text in this case to show how it works. So we declare an empty data type. We just care about the type level. We declare an instance for it. We have a constraint over there. That is that the T can be shown. So then we know how to serialize it as plain text just by showing it. And then this says, look, the type that I expect is an either T servant error IoT. So in the case of left, your handler might error for some reason. You can always return a left. You can always do I/O. But if everything goes right, you should return a T, whatever the T it is that you specified. And then we apply root. Those extra arguments come from routing application. We check that the path is empty because we've been cutting off parts of the path to get to the leaf node that are the methods. And if it's empty, then the URL matched. And then we also have to check that the method matched. And if the method matched, then we accept, which I'll show in a second. Otherwise, we say, no, this was bad, try something else. And then accept. The type of the handler is whatever we said that it was. We're free to choose whatever we want. So we just run our either T, which is what we asked for. And then if it matches, we set the content type and respond with 200. And then if it didn't match, then we say, oh, there was an error. Someone returned a left from the handler, so just give whatever error the handler responded with. So the handler is a simple Haskell, and completely non-special Haskell data type. We didn't even write it. And of course, I should say, the actual service implementations have a lot of other details going into them. But this is sort of a vague idea. And then we also have the alternative implementation. The basic idea is that whatever we expect from the left-hand side and whatever we expect from the right-hand side, we expect the combination of those as an argument once we see this. So if we have two handlers, if we have the combination of two gets, we expect the combination of those as the argument. And then, well, I won't go into details, but you try one and then you try the other. This might sound inefficient. Actually, benchmarks of head show that it's not. It's competitive with any Haskell web framework. And then there's capture, but I won't go into details because basically this is, by now, hopefully becoming sort of intuitive. It's just writing a web framework in the same way that you would before, but in the context of this entire infrastructure. So yeah, so hopefully I just wanted to give a sense for what the great advantage of having type-level DSLs are. And show that it works even for web frameworks are fairly complex, and it still works. It's still flexible enough to work quite well. And we have all of these interpretations that do quite distinct things, and we can still implement them as interpretations of a type-level DSL. So the notion of a type-level DSL sounds scary, but really we can do all these nice things, and they're these two properties that together are very hard to find, I would guess impossible to find in Haskell elsewhere. And so yeah, and of course I also do want to sort of play up at least a little bit the idea that with this we can write a new type of web framework. I think the reason why this was so hard before and why no one did it is because extensibility is really important. And so there are web API description languages, they're called, but they're hard to extend. So they become these protocols that are really complicated and whatnot. But if instead you have this extensible language that's a DSL and whatnot, you really manage to do it. And I think also the second component, which is varying the type that you expect, which you have to do unless you crush everything into something like the type of IO unit and lose all type safety. Because this is really type safe in a sense, right? You specify your DSL, and then you're forced to implement it in a way that accords with your specification, in addition to getting a lot of things for free. So there are all these things that work out really nicely from this basic idea of using a type-level DSL and interpreting in this way. Yeah, so thank you. I guess I have.
All right. So can you go back to slide number 10?
Number 10. Yeah.
10.
Oh.
Yeah. So I say, well, if I make a mistake here, I get type error.
Yeah.
So that's great. What does it look like?
A little bit of self-promotion, I suspect, no? I'll admit, it doesn't look good. We have some tricks that make it look, we can sort of stop how far the type error goes, because I've once made my computer stop working because of the type error.
Did you store that program anywhere?
Did I store the program?
Yeah,
no, I shut it down. I killed it.
I'd like to have it.
No, it was a really. We did at some point get really terrible type errors. Now we get bad type errors.
Because I can imagine that somebody who uses your servant API says, well, please get rid of the types now, because actually I prefer to run a unit test that gives me good explanation why something goes wrong instead of a type error that I really don't understand.
Yeah. This is one of the big problems that we still have, which is that we can enforce safety in all these ways that are really good, but basically what we're left with is, look, you did something wrong. Go back and figure out what you did wrong. We can't help you, which is a good point. Yeah.
Nice.
So earlier you mentioned that Haskell does not yet have dependent types. If it did, how could you make this even more awesome?
Yeah, so when we were writing a paper about this, and we sort of gave some thought about how it would work in a language like Idris or Agda. And really, for us, the type classes are sort of an important aspect of it. So you'd still need type classes.
So Idris has type classes?
Yes. So it would actually not look that different. One of the big differences is that instead of having this explicit associated types in them, you could just do sort of more regular value level and then figure it out afterwards. We didn't give it enough thought to come up with a definitive answer either way, but we didn't see anything that was obviously much better with dependent types.
So can I make a quick suggestion of something that might be cool to do?
Yeah.
So if your DSL was encoded as an explicit value rather than as a type, and then sort of interpreted as types in a sort of typical way, you could potentially read one in at runtime, and so you could use it on both sides of the phase distinction, right? So read in an API description from the user, and then immediately be able to call that API, all of it safe, rather than sort of having to recompile your program to get the safety.
Yep. Great, thanks a lot. The work in Servant was joint work with Zonke Han, who's over there, and Altmestano Gulari. Andres Loh helped considerably after the first release, as did the Haskell team at Anchor, which was one of the first commercial users of Servant. And I think this Servant is a particularly appropriate topic to discuss here because on the one hand, it's solving a very practical industry problem, namely writing web applications quickly and easily and safely. But on the other, it's using some ideas that, though they existed in some form in academia already, I think Servant's the first case that applies them in practice to a library. And these ideas, that's the type-level DSL side of it. These ideas are really interesting, and I also want to, in addition to discussing Servant as a library, also discuss this technique, which I think can be applied in a wide range of circumstances. So I'll talk a little bit about what it is that motivated us to do Servant, to what idea, what view of what web development should be like led us to try to write this library. And then I'll switch gears a little bit and talk about a much simpler, and give some examples as well of what it does. And then I'll switch gears and talk about a much simpler type-level DSL that hopefully will be much easier to understand and will really bring out the basic essence of the technique, and also the advantages therein. And hopefully, even if you don't use our library, you'll consider applying this technique in other circumstances. And then, to the extent that I have time, that's one thing that it has going for it. But currently, web frameworks don't do this. If you look at the code in the code written with most frameworks, the API itself is only implicit in the implementation. There's the routing section, and that's part of what the API is. But the rest of it, what the request body looks like, what the response body looks like, what the headers that are expected, they're strewn all over. The handler handles part of it, the routing handles part of it. And we wanted to, and it's an unfortunate circumstance, I think. Now, the second reason is that it's much easier to modify. With the description of the web API, if you change something, at least in the case of Servant, you get type errors wherever things need to be modified. And for those of you, I'll also talk about how we implement it practically, how we transform these ideas and transfer them into the context of web development. So let's talk about the main idea. The main idea is roughly this. In web programming, web APIs should be a central concept. The description of a web API in particular should be a central concept. And in a sense, this is already the case. If you observe, if you witness people working on APIs, web programmers will very often talk about their API and discuss it at great length. And in fact, often that's the business requirement is, this is the API, this is how it has to look. And so in a sense, making that central, it accords with the practice of development. And that's another who are Haskell programmers or Camel programmers. This will be a familiar and very desirable trait of programming in these languages. But the third reason, these are both sort of, you'll have to take my word for it, or you'll have to experiment and see whether you agree with me points. But the third one I hope to make very concrete and might be the most important. And it's that web API descriptions are a reusable component, and one that we want to reuse. We want to reuse it in a variety of circumstances. When we're writing a web service, we want to be sure that we accord with the specification, and we don't want to repeat ourselves about the aspects that go into it. When we're writing documentation, we also need it. And I'll show you some examples. Documentation will be the first one. To make this more concrete, I'll give a simple example, a simple running example of a service that just wraps a counter.